Our first talk will be by Devansh Jalota on when efficiency meets equity in congestion pricing and revenue refund schemes.
Hi, everyone. I'm Devansh Jalota, and today I'll be presenting our work on when efficiency meets equity in congestion pricing and revenue refunding schemes. So as we all know, traffic congestion has become very much a commonplace part of daily travel in large urban metropolises all across the world. And this has led to a large amount of lost hours in the time that users spend in traffic jams, as well as massive economic losses in various different sectors of the economy. As a result, congestion pricing, wherein we place tolls on certain roads of our traffic network, has been hailed as a means to alleviate some of these issues of traffic congestion. And in fact, the effect of congestion pricing can be depicted through the following simple diagram, wherein as we raise the tolls on certain roads of our traffic network, we're effectively decreasing the total amount of traffic volume that will pass through those same roads. And as a result, we'll end up increasing the level of system efficiency or decrease the total system cost or travel time within the system. And one very key and important thing to note with congestion pricing is that with the advent of autonomous transportation, it is only likely that intelligent system-wide road pricing is going to become more attractive over the coming years. However, despite the efficiency benefits of congestion pricing, one of the major issues with congestion pricing is its corresponding social inequity issues, wherein low-income users may be priced out of certain roads within the traffic network. And in particular, to describe this effect, as we increase the tolls on certain roads of our network, users who were originally able to use the same roads are no longer able to do so because it's potentially too costly for them to afford to be able to use the same roads. And as a result, we have resulting social inequity issues. So essentially, because of these social inequity issues, this has led to a move towards the design of more equitable mechanisms that not just look to collect the tolls collected through these congestion pricing mechanisms, but in fact look to refund and redistribute these collected toll revenues to the right groups of users within society. And in fact, this particular concept, which is broadly termed as congestion pricing and revenue refunding, which I will henceforth denote as CPRR as a shorthand, has been studied now for over the last few decades. However, there has really been no thorough characterization of the wealth inequality effects of such schemes. And as a result, this has precluded the design of CPRR schemes that are specifically catered to improve wealth inequality outcomes within society. So within this particular work, we look to plug exactly this gap within the literature by studying the wealth inequality effects of CPRR schemes. And we do so in the context of non-atomic congestion gains. And in particular, we're looking to design schemes that simultaneously improve upon the equity and efficiency outcomes within society. And while improving upon both these measures of equity and efficiency, we also want to make sure that our design schemes are publicly acceptable for all users, which is to say that no user should be worse off after the implementation of our schemes than they were prior to the implementation of the scheme. So this is essentially a simple individual rationality condition that we want to make sure that we're meeting. And it's described by the following diagram, wherein the cost for all users after the implementation of the scheme is no more than their cost prior to the implementation of the scheme, which is given by the no tolls or refund setting. So as a whole, we're looking to design schemes that improve on the social, on the system efficiency and wealth inequality objectives, while also being practically deployable through this notion of what we call a user favorable or an individually rational scheme. So I'm going to move into our model. So in particular, to describe our model, first I'm going to introduce the notion of a user group. So in particular, all users in society are going to be grouped based on certain characteristics. And in particular, we're going to first classify users based on those who make trips between the same origin and destination pair as depicted by the different colors on this diagram. And then for users within the same OD pair, we're going to further classify users based on those having the same values of time and the same levels of income. So essentially, users that belong to a given group have exactly the same origin destination pair, have the same value of time and the same level of income. And that's exactly how we classify user group in our work. So having defined the notion of a user group, I'll now describe what the cost function of each user within that group looks like. And in particular, within this work, we assume that users incur a cost that is a linear function of their travel time, their tolls, and their refunds. So I just need to introduce a little more notation to elucidate the travel time function. And in particular, we're going to let xe denote the flow on a given edge. Then the travel time function is a flow-dependent travel time, which is denoted as te of xe for that particular edge. So that's the amount of time that I take to traverse that given edge within the network. Then with this notation, we can now define the travel cost for every user within a given group as mu g, which is for a given group G, we can define the travel cost as a function of the tolls that are placed on each of the different edges within the network and the refunds that are given to each of the different user groups as the following. So the travel time component of this cost function consists of a value of time. So essentially all users within this group have the same value of time, V sub G. And this is essentially just a way to monetize the travel time cost that users are incurring so that we can put that in the same units as the tolls and the refunds. And we're just going to weight the value of time with the travel time that they incur, which is just going to be a sum of the travel time on all the edges within the path that the user uses. Then the toll component is relatively simple. It's just summing across all the tolls on the given path that a given user uses. And finally, the refunds are something that the users receive. And thus, in our travel cost function, we have a negative of the refunds because this is a quantity that each user receives rather than incurs. So just a couple of important observations about this particular cost function. So the first thing we must note is that we cannot have a situation wherein the sum of the refunds given adds up to more than the tolls collected. That's a very simple feasibility condition that we must meet so that we're not violating this constraint. And secondly, one thing you may have noted is that in the notation, mu g of tau r for the cost function, I don't have any dependence on the path. And that is primarily because in this work, we're concerned with equilibrium flow patterns. And thus the specific path that a user uses is irrelevant in the formulation of the travel cost, since all users within a given group at equilibrium will incur the same travel cost as long as the path has positive flow for that given user group. So having defined some of these, the notion of a travel cost, now the next thing what I want to do is formally introduce the metrics that we use in order to evaluate any CPRR scheme within this work. And in particular, we're going to use the metrics of efficiency and wealth inequality, which I've mentioned earlier. So in particular, for efficiency, we're going to evaluate efficiency through, for any given traffic assignment, which is just a vector of edge flows for the different user groups through a notion of a total system cost. And essentially a total system cost is defined as the value of time weighted travel times of all users in the network. And so just to take this a little more slowly, we can think of just consider every user in our system. What is their value of time and what is their travel time? We're going to multiply those two quantities and sum this across all of the users within the system. And that gives us a quantity known as the total system cost. So that's how we're going to measure the efficiency within the system of a given CPRR scheme. And then to define the wealth inequality, I'm going to introduce a new definition called the ex post income distribution of users, which is essentially what is my level of income after I have completed a trip, given that a CPRR scheme, tau r, has been implemented in society. And that is essentially given by a very simple update equation, which is what is my level of income prior to me having started the trip, and what is the travel cost that I incur during the trip. So my level of income that I end up with after is just what is my initial level of income minus travel cost, and that's exactly how much I end up with after. So with this definition of an ex post income distribution, we can define or measure wealth inequality of this particular ex post income distribution after the implementation of a given CPRR scheme. And what we're really interested in is comparing this level of wealth inequality to that of the status quo traffic equilibrium pattern. That is, are we really improving in the wealth inequality measure relative to, say, the no tolls or refund setting which exists in society today, or not? And so essentially, this is how we're going to measure wealth inequality within our particular work. So now to go on to the main results of this particular work. So in particular, the first main result that we show is that for that there in fact exists a user favorable CPRR scheme, which is basically a scheme in which no user is worse off after the implementation of a scheme than they were prior to the implementation of a scheme, wherein we're able to show that there's such a scheme that simultaneously improves outcomes in terms of system efficiency, which is we achieve a lower total system cost than the status quo, as well as achieve a lower level of wealth inequality as compared to the status quo traffic equilibrium pattern. And essentially, because we improve on both the efficiency and equity metrics, we refer to this particular CPRR scheme as Pareto improving, since we improve along both of these different measures. And I'd be happy to talk more details about the exact proof strategies and so on, but I think this is probably too short a talk to go into many of those details. So the second result, which is, I would say, the main result of this work, is that we're in fact able to show that there exists an optimal CPRR scheme. And it's a priori not even obvious that an optimal scheme even exists in this context. But what we're able to show within this work is that there in fact exists a scheme that achieves the highest level of system efficiency possible, which is essentially the lowest total system cost that could be possibly achieved, as well as this scheme also simultaneously achieves the lowest level of wealth inequality possible among the class of all user favorable CPRR schemes. And so essentially what we're able to show with this result is that while efficiency and equity are typically thought of as being at odds with each other, in fact, at this optimal CPRR scheme point that I have in red here, we can actually make both efficiency and equity meet with each other. And that's essentially, I would say, the major result of this work. And just to give you a little more description on this, in fact, that to compute this optimal CPRR scheme, we can give a very simple two-step prescription in order to, which is also very intuitive, in order to actually find this optimal scheme. And in fact, the first step is just computing the optimal set of congestion tolls that induce a traffic equilibrium pattern with the minimum total system cost within society. And the second major step involved in this is that once we've collected the set of tolls, then how can we actually optimally refund these collected revenues while ensuring that we're satisfying the user favorability condition? So essentially, what we're concerned here with is that we want to make sure no user is worse off after the implementation of the scheme than they were prior. And so we need to make sure that we're being feasible with respect to that constraint, but also you'd like to optimally refund revenue so that we're minimizing wealth inequality as much as possible. So essentially, this is sort of a description of the optimal scheme and how we could possibly compute it in real world applications. So just to wrap up, essentially within this work, what we've been able to do is make some steps towards progressing towards both the equity and efficiency goals of sustainable transportation. And what our hope is that with this work, we're able to start a move towards changing some of the attitudes towards congestion pricing and shifting the discussion around congestion pricing from one that is largely focused on the societal inequity impacts of congestion pricing to one that now really thinks about how can we best use the collected toll revenues to in fact reverse some of these wealth inequality effects that we normally associate with congestion pricing. And so that's a hope that we have from our particular work. And just some outlines on possibilities for future work. So the first thing that I think would be particularly interesting is to actually extend our framework and model to apply to multimodal transportation systems, wherein we don't just consider one form of transport, but in fact, different types of transport that are now gradually picking up in society today. Secondly, our model currently only thinks about direct lump sum transfers of refunds to users. But what if we consider other elements of the pie, wherein we look at how much can we transfer some amount of this to public transit, to developing tolling infrastructure, or for other different purposes that currently haven't been accounted for. Then other interesting applications include accounting for electric vehicles or autonomous vehicles within our framework. So for instance, in the case of electric vehicles, you could think of creating an entirely new user group for people having electric vehicles and giving them refund benefits, for instance, because they are being more environmentally conscious or beneficial. And on the other hand, in the case of autonomous vehicles, we can think of connected fleets of autonomous vehicles, wherein we also need to account for things like rebalancing constraints that currently are not accounted for in our model. And it would be great to see if some of the results that we have still apply to these more complex and interesting settings as well. So I'll just leave with the slide, and here's my email and link to the complete version of our paper. And I'd be happy to take any questions. And thank you so much for listening.
Thanks so much for this talk, and thanks for being on time, or even a little bit ahead. I would like to remind everyone who's in the audience that you can ask questions in the Q&A or in the chat during these talks. That'll help me get a good, quick question in to this tightly packed schedule. I don't see any there. So the one that's really been on my mind the most, and was kind of alluded to in the end with your electric vehicles, is there room to bring in some kind of environmental concerns as well? And so when you're thinking about all of these different parties, also thinking about like people who use bicycles or other renewable means for commute, people who live close to work or telecommute. And is that something that you might extend this to? What are your thoughts?
Yeah, so actually just going back to this slide, so I think basically you touched on both the electric vehicle and the multimodal forms of transport with your particular observation and question. And I think that definitely, I guess, to further translate our work to something that is more closer to, say, real world applications, ideally we would want to be able to take some of these considerations into account, because I guess if there are users who are willing to, say, just bike to work instead of, say, taking a high toll road, potentially you could think of the refunds in the sense that I'm collecting the tolls from, say, high income users who are still wanting to use cars, and instead just transferring it to low income users who are using bikes to travel to work, for instance. And so definitely, I think that those would be very important considerations that should be accounted for. I would say the one nuance or interesting thing that happens when we account for multiple forms of transportation particularly is that our travel time function that I mentioned starts to look much more complex because we don't just have one form of transportation. So we need to think of what the interaction is between these different types of transport, and also within each type of transport, what is the exact travel time function for that given, I guess, edge in our network. So I guess that's as far as this is concerned, which is where I see, I guess, at least a technical difficulty in extending some of this work to multiple forms of transport. But at least maybe doing sort of some type of numerical simulations may be a good starting point on that front. And as far as electric vehicles are concerned, just a quick note that I guess electric vehicles can still very much be modeled as standard vehicles in terms of travel time functions to a large extent. And so we could very much just add in an entirely new user group based on whether you have electric vehicles or not, and potentially give environmental like refund benefits and things like that for these groups of people. Yeah.
Well, thanks so much again.